Hello everyone, this is Professor Chan from Math 1245 speaking. Today we're going to be going over section 3.1, dealing with parabolas. So throughout this chapter, we're going to go over parabolas and go over something called polynomial graphs. So that's going to be the main extent of chapter 3. But 3.1 specifically, we're going to do what's called parabolas or quadratics, as you may know it. Um, this section will probably be split into two videos right here. So let's get started. So let's just remember what a parabola looks like, right? Y equals x squared. And it looks something in the minds of this, right? So it's a U shape, and specifically, we also know that it is symmetric. It looks like this, right? It's opening upwards. It looks like this, okay? And then, so we have something called our maximum or our minimum, depending on which way our parabola is opening up. So in our case, if I look at my graph here, right, in our case, I have a minimum like this, right? It's my smallest point across my parabola. Or if I have something like this, I have what's called a maximum, which will look like something like this here, okay? Okay, so depending on kind of whether it's opening up or down, it's either a maximum or a minimum. They're both called something called a vertex. Our vertex is what's called 0, 0 for the following here. Okay. And then we have something what's called the line of symmetry. So what is that? It's essentially the line that cuts my parabola in half. So idea is I have a line of symmetry like this. In our case, it's vertical. And it crosses through, and it crosses through at x is equal to 0. Okay? And then read this part here. It's always going to be x be some number, okay? Because it's a vertical line. Later, you'll see this. It'll probably be transformed, but we won't get to that till a lot later in the chapter. Okay, so moving on. Let's talk about some other basics for a parabola. Okay, we know that it also opens up. Okay, and then an important thing is if the x's are the same distance from the vertex, and when I say same distance, I'm talking about horizontal distance. They will have the same y values, okay? So what do I mean by that? So, and if you look at the paper, it says example 3, 9, 3, 9, and negative 3, 9. So what do I mean when I'm talking about that? So when you look at a parabola, right, I have 3, 9 here and negative 3, 9 here. Both of them are 3 away from my vertex horizontally, or you can almost think of it as 3 away from your axis of symmetry. So because of that, they both have the same y value, okay? And this is something important for us to know because it's going to help us in the long run when we graph parabolas. So other than my vertex, right, or my max or my min, every other point in a parabola is a pair. So essentially, you'll have 2 points that are going to be equal distance from the vertex that will have the same y value. So other than the vertex, everything else will be there'll be 2 points kind of matching each other because it's symmetric. Okay, so let's talk about transformations for a parabola. We have, now if you think about this here, last time we did transformations, right, we had vertical shifts, we had horizontal shifts, but then we add flips and stretches. Okay, so the same thing actually applies to a parabola, and we should kind of notice already. We actually kind of practiced some of this back in chapter 2, but let's take a look at this. Remember, if you have a object inside of parentheses and you're adding subtracting, right, it is horizontal, right? So H is your horizontal shift. This is the one that always trips a lot of people up. It's always backwards. So if you're adding, you're actually going to the left, and if subtracting, you're going to the right. Okay. If you look at letter K, which is adding or subtracting outside of parentheses, this is the vertical shift. So if you're going positive, it's up. If you're going down, it's negative. Okay. The number in front of the x square is your stretch. And specifically, we're only focused on vertical stretch. We're not going to worry too much about horizontal. Okay, stretch and compression. So if A is less than 1, we do what's called a vertical compression. And if A is greater than 1, we'll do a vertical stretch. Okay, let me actually just zoom in a bit to make things a little bit better. Okay. Yeah, it will be a vertical stretch. And then if my A is positive, so I have a positive in front or a negative in front. If it's positive, it's opening up. If it's negative, it's gonna look like this, right? It's gonna flip down. Okay. For the following here. Okay. Okay, so those are your basics for a quadratic. So let's do some examples here. Okay. So if I want to graph this, okay, let's just talk about the transformations for a graph, okay? So this should be kind of familiar to you guys back in chapter 2. So if you're being asked to graph this and you're being asked to do this by hand, right? One thing you have to remember is, right, remember your original parent graph, right? Everything's going to be in terms of the form y equals x squared, right? So it's going to be like this. Okay? For the following. Okay, now let's talk about our order of operations, right? So for number 1, I have 2, right? Now I want to make sure I remember I go in order. So multiplication goes before addition, subtraction. So I'm going to do a vertical flip, and then I'm going to the right by 2. So if I do my flip first, remember that means my y gets flipped by -1. Or multiplied by -1, so it'll be -2, -4, -1, -1, 0, 0, 1, -1, 2, 1, -1, my bad, 2, -4. Sorry, let me fix that. Right, and then the next step, I'm going to go to the right by 2, so that means I'm adding 2 to x. So this is 0, 1, 2, 3, 4. Those are my points, okay? So we can graph this. And see if it matches. Okay, definitely matches. Okay, If I look at my table, yep, that looks pretty good right there. Okay. Now, sometimes you'll also be asked to find the vertex and the axis of symmetry. So the idea is your vertex and your axis of symmetry can also move as well. Now, earlier in the notes, it says your vertex does not move through stretch or flips, but it does move by shifts. So let's talk about this. This is where your vertex was originally. And then notice where your vertex ends. So your vertex is going to be 2, 0. And then your axis of symmetry is actually going to be the x-coordinate of your vertex. So you'll say x is equal to 2. Okay. Okay. Yeah, now let's look at one more example. Okay. Feel free to work on more of these by yourselves, okay? But you should have a good handle on this because this is kind of familiar to what we did in, I think it's section 2.5 in the videos. Okay, but if you have trouble, yeah, just practice that section. It's gonna be very helpful to you. So my transformations is right by 6 and then up by 4. So technically it doesn't matter which way you do these first, okay, because they're both addition. So right by 6 means I add 6 to all my x's. So negative 2 plus 6 is 4. Negative 1 plus 6 is 5. And then I'm going to go up by 4. So I'm going to add 4 to y. So 4, 8, 5, 5, 6, 4, 7, 5, 8, 8. Okay. So your vertex is right here, and then notice where it ends up. So my vertex is 6, 4. And my axis of symmetry is x is equal to 6. Now here's the thing. So take a look at the following, right? So if you notice that there's a lot of work being involved in order to find your vertex, if you're doing your transformations, but if you look back at your functions, it kind of gives it away, right? So if you notice, if you look back at number 1 here, I'll do this in orange, right? This is x is equal to 2. Sorry, this is 2, 0, because I'm shifting to right by 2. And notice for number 2, negative 6 and plus 4, so it's 6, 4, right? Move to the right by 6, 4, right? Because my vertex is 0, 0, so I moved 6 to the right and then 4 up, so it'll be 6, 4. So if you kind of look back, you can actually easily identify where your vertex will be. And then once again, your vertex only gets moved through your shifts, not your stretches or your flips. Okay. So that's how we would do transformations, right? And then once again, if I graph it, I can see that this will match up. And that will be my answer, right? And I can graph it on a graph sheet of paper. Okay. Now, let's talk about this situation right here. Okay. This is definitely the trickier situation. So the thing is, if you notice, all the problems that we did before are in what's called its transformative form. So it's like the numbers out in front, I have x plus h squared plus k, right? These problems here have these. But notice if I go to a problem like this, it's a completely different story. I have x squared plus 8x plus 15, right? There's nothing in parentheses, right? There's nothing factored out, okay? And so that's kind of problematic for us because we need that to figure out what our transformations are and what our vertex are for the following, okay? So let's get started. Okay. So I'm going to make some room. One thing too is when you're taking your notes, you want to actually kind of like write on a separate sheet of paper because you may not have room on these printed handouts. Okay. So let's talk about the following here. So it says converting a quadratic function into the following. So, and what we're going to do is we're going to put our first two terms, assume that make sure your quadratic is going from largest to smallest in terms of degrees before you start, right? So we're good because it's x squared and x and a number. So what I'm going to do is I'm going to group the first two terms like this here, okay? So what am I doing? I'm actually going to complete the square inside, okay? This is where section 2.8 is helpful because we want to complete the square. So remember, what I do is I'm going to do 8 divided by 2, and then I square it, and it'll become 16. Okay, make sure you practice this, otherwise you're going to fall behind with this right here. So I'm going to add 16 for the following here. Okay, now, this is where it gets a little odd, okay? Because I'm only doing everything on one side. So notice, right, the f of x on the left, I don't really want to manipulate that. So I can't just be like add 16 both sides. So what I want to do is do the opposite on the other side. So I'm going to say plus 15 minus 16 like this, okay? So let's understand, right? I'm putting 16 into my function. I cannot just do that arbitrarily, right? I can't just randomly throw that in and think that's okay, right? Because that throws everything off balance. So I would say plus 16 and then minus 16, right? Because what happens is essentially is I'm actually adding 0 technically, okay? So I say plus 16 inside parentheses and then minus 16 outside. And it's going to look like this. So we're going to factor it. This becomes x plus 4 squared. Yeah, and again, make sure you know how to factor. And then 15 minus 16 is going to be negative 1. Like this. Okay. So, number 5 says list your transformations. Okay. So, the transformations I have is the following. I'm going to the left by 4. And I'm going down by 1. And then they may ask you what your vertex is. My vertex is going to be negative 4, negative 1. And then my axis of symmetry is x is equal to negative 4. Okay? And that's it. And then we can do the transformations. We can graph it. But hopefully you guys should have a general idea. Okay, the focus is we're going to manipulate these functions so it's in what's called the transformative form. Okay. Now, what happens if I have something like this here? And this shouldn't be too much of a new thing to you because we did something similar with circles. Okay, so I'm just going to space this out right now just so that I'm giving myself some room. So, same thing, I'm going to group my first two. Now, the thing is, remember, like what we talked about with circles, we cannot have a number out in front, right, with this x squared. Otherwise, I can't factor it, right? Perfect squares, it's easier to have perfect squares with just x squared and no number in front. So I'm going to pull out my GCF, the number only, okay? Don't pull out the x, just pull out the number. And I'm going to do it like this. Right, I'm dividing each one by 2. Okay. So, what is my n term to complete the square? This is going to be 4. Okay, make sure you know how to do that. Right, negative 4 divided by 2 is 2. 2 squared is 4. Okay, for the following here. And I'm going to add or subtract something, right, to balance it out. Now, let's talk about this one here. This one's a tricky one. You're not really adding 4, you're really adding 8. So because of that, we need to subtract 8 to balance it out. Because I'm adding 8 inside, and I'm subtracting 8 inside. And then I'll factor it. Okay. And I have the following. So my transformations is, remember multiplication goes first, so vertical stretch by 2. I'm going to go 2 to the right. And then down by 3. My vertex is going to be 2 comma negative 3. And then my axis of symmetry is going to be x is equal to 2. And that would be it right there. Okay, so let's continue on working some more problems. Okay. Yeah, so we'll do 2 more examples for the following, okay? Let's do number 3 just because it's a slightly more difficult one here. Actually, let's do 4. So, we're going to do the following. Make sure they're in order, group the first 2. Remember, I do not like numbers in front of x squares because, within the parentheses, because it's really difficult to do perfect squares with those. They both are divisible by 4, so I'm going to pull out a 4. So 4 divided by 4 is x squared, negative 12 divided by 4 is negative 3x. Okay, and then I'm going to think of a special number that is going to make this a perfect square. Okay, now unfortunately for us, this is kind of a brutal one because this will be a fraction. Negative 3 divided by 2 is negative 3 halves. I square it, it'll become 9/4. Like the following. And I'm trying to think about what do I add and subtract to balance that out. Now let's think about this right here. Okay. Yeah, so this one's kind of an odd one. Okay, so let's take a look at this. So I'm adding 9/4, but this is inside being multiplied by 4. 4 times 9/4 is 9. So to balance it out, I'm going to subtract 9. 4 times 9/4 is 9, and I'm going to do the opposite. So it's going to be negative 9 for the following here. Now, what does this factor to? So trick is, okay, I know fractions can be difficult. You take the square root of the end, or you divide the middle one by 2. So negative 3 divided by 2 is negative 3 halves. 9/4 square root is 3 halves. Always look to follow the middle sign. So minus, and this is 3 halves. And x squared 9 plus negative 9 goes away. So let me rewrite that again. This is my final answer. What are my transformations? So I have a vertical stretch by 4. And then I'm going to the right by 3 halves. So what is my vertex? Okay, so if you notice, there's no addition or subtraction outside, so my y-coordinate is 0. And then my x-coordinate is 3 halves. And then an axis of symmetry is x is equal to 3 halves. So let's end with one more problem. Actually, you know what? Let's do 2 problems. I'm going to go with number 6 here. Actually, you know what? Let's do number 7. Sorry, my apologies for just kind of jumping around. So I have f of x is equal to negative 3x squared minus 6x minus 1, okay? I want to do this one just because we have a negative in front. I'm going to group them. I do not like the negative 3, so I'm going to divide everything by negative 3 or factor that out. 6 divided by negative 3 is plus 2x. Sorry, I'm going to... And then this is going to be minus 1. I want to think about what I'm going to add inside here. Okay, so we got to be really careful with this one because we have a negative out in front. So 2 divided by 1 is 1. 1 squared is 1. Now, be really careful. I'm doing negative 3 times 1, right, which is negative 3. Negative 3, so that means I'm really adding negative 3. So I'm going to add 3 to balance it out. Okay, so let me say that one more time. If I put the 1 inside, I'm really subtracting 3, so I need to add 3 to balance it out, because negative 3 times 1 is negative 3. Okay, so this will be the following. It'll be x plus 1 quantity square, and then negative 1 plus 3 is 2. How does this one look? It's going to look like the following. My transformations are a flip, a vertical stretch by 3. Okay, remember the negative has nothing to do with the vertical stretch. The negative is a flip, and then a 3 is a vertical stretch. So there's 2 transformations within that number in front. Okay, going to the left by 1, and then up by 2. What is my vertex? You should get a hang of this by now. So it's opposite. So it's negative 1 here, and then up by 2. Okay. So yeah, remember, right? Inside parentheses always opposite what you think, but then the 2 is the same for the following, and then axis of symmetry. Is x is equal to negative 1. Okay. And that's it. Okay. I'm going to do the very last one, number 9, because number 9 can be a tricky one as well. So same thing. Once again, I'm going to group these two. The first 2 always gets grouped together. Be very careful when you pull out the 1/2 because you're dividing by 1/2, so that means you're actually multiplying by 2. 2 divided by 1/2 actually becomes 4. Okay. So we need to think about our special number that makes it a perfect square. It's going to be 4 this time because 4 divided by 2 is 2. 2 squared is 4. Right? And then once again, if you're not sure, okay, make sure you kind of follow this rule right here. Now remember, actually let me just rewrite this part again. So I am adding 4, which is being multiplied 1/2, which is 2. So I'm adding 2 inside. To balance it out, I subtract 2. So I'm going to factor this as x plus 2 squared and then minus 3. So transformations. This is a vertical compression by 2, left by 2, and then down by 3. And then, yeah, sorry. And then my vertex is going to be -2, -3, and then axis of symmetry, x is equal to -2. Okay, so we're going to end this right here. That's the first half of 3.1. That one is quite intense, okay, but make sure you practice this. We're going to come back. We're going to finish the rest of 3.1, okay? But other than that, I will see you guys later.